All right, well, let's look at this. I gave you all enough time to, to look at it. Okay, in this first one, let's give ourselves some room to work. Again, anytime you see multiple steps, break it out, do it step by step. So the first thing that's going to happen is we're going to form the enolate. All right, so remember this whole chapter, we're either forming an enolate or a enol. So once we have that, we can react that with our electrophilic carbon. Again, drawing this out can help us make sure that we put it in the right location. And we can go ahead and number this, right? So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, right? And then we have the center carbon on the other one. So if you want to mark that one right, this is the alpha. That's the alpha. So we add alpha to a 1. Okay, then what on this one, the thing that you need to really watch is this second step, right? And the second step here is just water. So what water is going to do is just allow this to go to this product. So it's just going to take care of any base issues, right? So in this case, this will not hydrolyze it. And so this is one of the things that's going to come up when you look at it. Right? The other one, if we look at this one, right? First, break it into its steps. So the first step, we make the enolate. Then that enolate is going to react with our electrophilic group. So draw that so you can get it in the right location. That gets us back to this. Now we have acid and water. So the first step with the acid and water and heat, right, is going to be to hydrolyze this. So we hydrolyze the ester to the acid. And then once we have an acid in a 1,3 arrangement with a carbonyl, and we add heat to that, we can do a decarboxylation. Okay, so that's the malonic ester. So the first one was like an acetic ester, but I didn't do the hydrolysis, decarboxylation. The second one is a malonic ester synthesis. Questions about these? Yes, ma'am. Yeah. Okay, so we finished up through the aldols, clasons. We did the malonic esters, decarboxylations. We're going to look at a couple more sections. We should be able to finish the chapter today. So conjugated additions. So remember that if we take if we do an aldol reaction, but we also add heat, that we can end up with the alpha beta unsaturated group. And so what this one's going to be looking at is if we look at this, right? Don't know why I'm still in blue. We can show resonance for this. where we break that pi bond to give me the positive and negative, right? So we're breaking this pi bond to give me this charge separated species. But we could also, right, move this electrons here, right, so that we can have another resonance contributor with the positive here. Okay. If we look here, we usually refer to this as direct because it's at the carbonyl. And there's a positive, partial positive there, or positive, because this is all resonance contributor. And then we have one at the beta position. So we actually have two potential electrophilic additions if we had a nucleophile to attack this, right? So if we had a nucleophile coming in, the nucleophile could attack at the direct position. Keep our color scheme going to give me this, or the nucleophile could have reacted at the beta position to give me this. So with alpha beta unsaturated species, if I attack them with a nucleophile, I have two possible pathways. And the question really comes down to what's going on, you know, what type of nucleophile do I have? If we look at the molecular orbitals of these two pictures, it actually helps us quite a bit. And so there's two ways to refer to this in chemistry. We can refer to it from a molecular orbital a density, but if we look at these two, which of these two do you think is going to have the greater the most electron deficiency, the greatest positive? The one directly attached to the oxygen or the one that's delocalized from the oxygen? Well, because of the electron withdrawing nature of the oxygen, right? This one should have a higher electron density. So if we look at the molecular orbitals for this one will have a lower coefficient for electron density, or be more positive. This one will be less. The other way we refer to this, and this is an older term, but it's what I learned, is hard and soft. Okay. So you can think about where these attack by which ones have a hard nucleophile, meaning a high density negative charge, and which ones have a soft nucleophile. So we look at these two positions. What you want to do is have high electron density with really low electron density, and you want low electron density with moderate electron density, right? So getting them closer in proximity. Okay. So when we look at these, there's a few that work here. The book focuses mostly just on carbon-carbon formation. But if we look at our standard ones, if we do a reaction, and let me get back to black. Okay, so if we look at alpha beta unsaturated aldehyde here and react that with a Grignard, right, we're going to get direct addition. Okay. And the direct addition can also sometimes be referred to as the 1,2 addition, right? Similar to what we saw in conjugated dienes. If we react this with a cuprate, so our Gilman reagent, so our copper lithium reagent, we're going to get the beta addition. And again, sometimes referred to as 1,4 addition. Now on this one, let's show how this works, because it's not intuitive on why we end up with the carbonyl at the end. But our Gilman, right, we get attack at the beta position. And then when we get to this position, right, this is where we would bring in our proton source. Now, because protons and oxygens are closer, the fastest thing that happens here is actually the protonation of the alcohol. But the protonation of the alcohol is what? That forms an enol. And what do enols do? They tautomerize, right, to ketones. So the addition does give us this enolate type form, but then that enolate gets protonated to the enol, and then the enol tautomerizes back to the carbonyl. As I said, the book focuses on these two, Grignard's and Gilman. The other one that you'll see sometimes, and I'll show you this because it turns out to be biologically important, is cyanos. So we know that a cyano group will react with a carbonyl, but this is also a soft type nucleophile. And if I have an alpha beta unsaturated here, so let's say sodium, and then we need a proton source to finish the reaction, the nitrile will go to the beta position. And again, this is biologically important because I could take the nitrile and hydrolyze it, as we saw in the last chapter, right, to the carboxylic acid. So now I have a beta position here. I put a carboxylic acid on that beta position. Questions about these? So your Grignards are going to be direct addition like we've seen, but now the Gilmans are going to prefer the beta addition, and the nitriles will favor the beta addition. The other soft nucleophiles we have are actually enolates. Okay, so if we take a enolate, and let's make it just this one. Let's go ahead and put the title at the top. So the next one we have is the Michael addition, and this is a beta addition using a stabilized enolate. So the first, what this is going to do is add and I did not count my carbons. So let's look at this. So the first thing we're going to do with the base is form the enolate. So again, that's one of the mantras you should be telling yourself in this chapter is how did I make the enol? How did I make the enolate? That's usually the first step. The protons, this is that, remember this has a pKa around 9, so therefore it's much more acidic than the other two positions. So I form the enolate there. Because there's a difference between 16 pKa and 9, this will quantitatively make this, right? So I don't have to worry about it reacting with itself. Then I bring in my alpha beta unsaturated. Now this would normally react direct if it wasn't alpha beta, but if it is alpha beta, it's going to prefer the beta position. Again, because of the delocalization and this kind of soft nucleophile process. So let's draw that out. So we've reformed that carbonyl. Now we have a bond. So now we've made a carbon-carbon bond at the beta position. And then the last step is just to protonate that. So it's going to pick up this proton. Right, and then this is the enol form that's going to tautomerize. Back to the carbonyl. Questions? So a Michael addition is an enolate reaction. It's most often shown with the dicarbonyl species, right? So when you see a straight Michael addition, it's almost always shown with this 1,3 dicarbonyl species. We could also do it with a diester, but if we use the diester, we'd want to use the ethoxide. Okay. So you could use, something like this. And we'll go through this one. So we'd use the sodium. We'd use the sodium ethoxide versus sodium hydroxide here. Second step, right, we're adding our electrophile, which in this case is the alpha beta unsaturated aldehyde. And then the third step, let's do acid and heat. Well, I'm not going to show you the action. Let's think about it. So take a little time, work on this one, see if you can figure out what's going to happen, right? Form the enolate. That's your first step, and then see if you can come up with what's going to happen in this process. It's okay if you don't get all the way from it, just get started. What does the enolate look like? How does the enolate react with the electrophile? Again, do it step by step. Let's take a few more seconds and then we'll get started together. Again, feel free to talk to your neighbor. All right, let's look. So the first step is the enolate. So it's going to pull a proton, right? That's the most acidic proton. So that's the product of the first step. And then this is going to react with our beta position. Okay. Oops, I'm skipping a step. Let me not do that. So we have this enolate, right? So enolate is formed after the first, but then we're going to add, now we're going to step 3. Right, so let's follow this. So this is step 1. Here is step 2. Now we're starting step 3. And step 3 is going to have actually 3 steps in it, or 3 phases. So the first thing we have is the protonation. That's going to pick up our proton. And then we get the tautomerization. Getting back to the ketone. Okay, but what's going to happen in strong acid and water, or acid and heat? Strong water, acid, and heat. Well, now I'm going to have hydrolyze my esters. And then what happens with heat? The decarboxylation. So we form the enolate. The enolate reacts at the beta position. Right, then we have to do some transfers to get us to the back to the carbonyl, which is where we get here, right? We protonate to get here. Then under these conditions, right? And what's the key to the conditions here? The heat, right? That's going to tell me I've got a more severe conditions. So that means I've got a higher probability of hydrolyzing those esters. And if I hydrolyze those esters, I can decarboxylate. Now, one of the things to notice in these Michael additions are the additions of a carbonyl to a alpha beta unsaturated is we have a 1,5 arrangement. Remember that when we did Claisen reactions, we always ended up with a 1,3 arrangement of the carbonyls. Here we're ended up with a 1,5. It's kind of a key that we're going to be doing this. Okay, questions about Michael additions. The next reaction is called the Stork reaction, or Stork-enamine reaction. And it comes from the fact that if we put the same conditions what we're going to end up over here is we might end up with a little bit of this, but we could also end up, and for this one, let's take that. Oops, that's not what I meant to do. But we'd also end up with a little bit of this, and we'd end up with a little bit of this. And that's because what's happening here? Well, these two hydrogens, right? The pKa of these are about, 18 to 20, but the pKa of water is 15.7. So when we look at a Michael addition, we have that 1,3 carbonyl that drops that pKa, and we get an equilibrium. But if we try to do it here, the problem is what's going to happen with the sodium hydroxide. I'm going to end up with both the enolate and the original ketone in solution. So when I'm looking at, it would be great if we could do a Michael addition with just a single carbonyl species. But the problem with a straight Michael addition type process is that I'm not forming a quantitative enolate. And since I'm not forming the quantitative enolate, I can end up with a mixture of products. So that's where the Stork-enamine comes in. So what we do with the Stork-enamine reaction is, instead of trying to form the enolate, we form the enamine. So the first step, and we'll work through this, is a secondary amine with trace acid. We're going to add our alpha beta unsaturated species, and then we're going to add an acid and water solution. So the first step, we were going to make the enamine. So remember, if you take a carbonyl, react that with a secondary amine with a trace of acid, that's going to form this. So that's my enamine. So an enol with an amine instead of an oxygen. But an enamine can react like an enol. So if we look at the basic structure, an enol reacts by the oxygen. So if we look at an enol, it reacts by this lone pair coming down to give me this species, right? So we're going to do something similar with the enamine. The alone pair from the nitrogen are going to come down. That's then going to, the pi bond is going to go out, react with electrophilic beta position. Then we get the electrons flowing around to the oxygen. We get the positive nitrogen. And since I've been doing it before, let's do it here. That ends up getting us this. Now I'm not going to show all the steps here, but what happens if I take an amine? enamine, or a positive imine in this case, and put it in water and acid. That's going to hydrolyze to the carbonyl. So what happened in the last step here, let me pick a different color. Is that the water and acid does a hydrolysis right, and protonation of the enolate. Okay, questions about that? And I would go through the mechanisms, but remember the enolate, the imine hydrolysis is six steps. So if you'd like, go back and take a look at that one. You can come to office hours and I'll show it to you. All right, so what the Stork enamine reaction does is allow us to do a Michael by creating the enamine of any single carbonyl species, right? So we selectively form the enolate, the enamine, then the enamine reacts with alpha, beta, and saturated, okay? So let's try one. Again, form it, do the steps. So form the enamine, then have the enamine react with the alpha, beta, unsaturated, and then hydrolyze the enamine back to the carbonyl and protonate to reform your carbonyl, your other carbonyl. Okay, so let's go ahead and take a look. So the first step, we're forming the enamine, right? The enamine goes towards the internal because we have an aldehyde in this case. And then that's going to react with our electrophile, which is this alpha, beta, unsaturated. So the lone pairs come down. We're going to attack at that beta position. Oops, I left the oxygen off. No trouble drawing 6-minute rings. All right, so we get that position. And again, sometimes it's helpful to number these. So 1, 2, 3. And over here, 1, 2, 3, 4, right? So that it is our 2 and our 3 position that's connected. And then in the last step, we're doing the hydrolysis and the protonation. And that's going to end up giving us the aldehyde here. And the ketone. And again, these should all storquinamines are modified Michaels, so they should always give us a 1, 2, 3, 4, 5 distance between our 2 carbonyls. Questions about this one? The next reaction is a Robinson annulation. And it's going to be a Michael and an aldol condensation. But it happens all in one pot at the same time. So you take a dicarbonyl species like this, you take a ketone like this. Now it has to be a methyl alpha beta unsaturated. So it does have to have this species right here in sodium hydroxide, and usually heat is shown. And we'll walk through this, but your final product is the alpha beta unsaturated. So if we look at this here, 1, 2, 3, 4, 5, right? The 1, 5 is a giveaway that this is a Michael. And then if we look here, we have an alpha beta unsaturated. Right? And that's the key, that we have an aldol condensation. So let's look at what's happening. So the first thing we're going to form in this chapter, a enol or an enolate, right? So the first thing we need to do is form an enol or an enolate. Then that enol and enolate can react with our, I drew that wrong, our species here. So at this point, right, we have our Michael addition. And would we expect this enolate, right? So there's our 1, 2, 3, 4. Did I drop a carbon? I sure did. That's why you should count, because it's easy to drop a carbon. Okay, so here, let's count again. 1, 2, 3, 4, 5. So here we have our enolate form. Now, in this enolate form, would this enolate react with that carbonyl carbon? Well, what would be the distance? So here we'd have 1, 2, 3, 4. Are we going to make a 4-membered ring? No. But in the presence of the base, that enolate I can get that enolate to go from the internal to the external. So think about a proton transfer process, right? We pull one proton, we add one proton, we pull another proton. So we can get this change in the enolates back and forth, right? Promoted by the sodium hydroxide. Now we have an enolate that can form a 6-membered ring. So if we look here, right, 1, 2, 3, 4, 5, 6. So now we have that in the right formation. So we've transferred the enolate. This can come around, attack that. And again, sodium hydroxide and heat, right? This is the last F of an alpha beta unsaturated. So if I add heat to this, this is going to give me the condensation product. So the 1,3 here is set up for a Michael. And the base heat gives me the condensation. Robinson annulation is a pretty helpful reaction because it's doing what? Why would this be something that organic chemists would like? How many carbon-carbon bonds am I making? Well, I'm making one here, and I'm making one here. So I'm making 2 carbon-carbon bonds. And I'm doing what? I'm making a cyclic, specifically a 6-membered ring. Which biologically, they're stable, and biologically they have importance. 5s and 6s, sometimes 7 is what you see in biological because they're stable. And Robinson annulation is something that tends to show up. I don't always put it on a test, but I've almost always seen it on standardized tests. So I'm not sure why, but mainly because I think organic chemists like it. It's like they're, ooh, I like this because it does magical things like make 2 carbon bonds and a ring. So, okay. Next step, synthetic strategies. So lots of reactions in this chapter, lots of carbon-carbon bond forming reactions. I would start doing the practice problems, but there are a few things to watch for while you're going through this. You know, if you notice, right? So if you're looking at a difunctional species, so if you look at a 1,5, right? What should a 1,5 suggest was a potential pathway? I potentially had a Michael, right? Or I had a stork. If I see a 1,3 and a 3 hydroxy, right? That should tell me that I'm looking at an aldol. If I see a 1,3 carbonyl species, and here I have an ester, but it turns out I could have turned that ester into something else, right? That's telling me that I should look towards a Claisen. And then the variety of the aldol here is if I'm looking at, so there's some structures, right? And if you're looking at an alpha beta unsaturated, then that's an aldol condensation. So there's some structures to look for when you're looking at synthetic strategies, right? So a 1,5 is a dead giveaway that you're dealing with a Michael or a Stork, right? You don't see the 1,5 carbonyl in a Robinson annihilation because it then reacts again, you know, but potentially a Robinson. The 1,3 hydroxide, that's an aldol, right? The 1,3 dicarbonyl, that's going to be some type of Claisen reaction. And then the alpha beta unsaturated is the aldol condensation. So these are some things, structural aspects to look for when you're looking for synthetic strategies. And we'll do some practice in a second on these. Now we've looked at alkylation of the beta position, right? You form the enolate and have it react with electrophile. And we looked at alkylation at the alpha position. We looked at the alkylation of the beta. So if we think about, you know, this species, we need to form the enolate. Right there, I get alpha alkylation. If we look at what we looked at earlier, right, if you take the alpha beta unsaturated, reacted with a Gilman, followed by, you know, water or water and acid. And this is the beta addition. But you can also do an alpha beta addition by combining these two. So the first step, you add your Gilman, which is going to be a beta addition. Second step, instead of using water, you use an electrophile. So instead of reprotonating, we're actually going to have the reaction again. We're going to need to look at this one so you can see what's going on. So with alpha beta unsaturated, first step, this is going to come here. Okay, but notice whenever we have the Gilman attacking the beta position, we get the electrons move around to the oxygen. What's this functionality right here? This is an enolate, right? What can an enolate react? Well, I could protonate it, form the enol, and then the enol tautomerizes the carbonyl. But what the alpha beta addition strategy is to add the electrophile, right? So we added electrophile in the second step. Now that just reacts. Questions about this one? So the product of the Gilman is the enolate, so I just capture that enolate and allow it to do the alpha addition. So that's the end of the chapter. So let's do some try this. Okay, let's take some time. Again, feel free to work with your neighbors. Look back at your notes. Probably not enough time to do all of them, but let's take a look. In the first case, we have an alpha beta unsaturated. I'm adding both a carbon at the alpha and the meta, right? So I'm adding at the alpha and the beta, right? This is the one I just showed you. So first we want to add the cuprate. That's going to be I did these backwards. Thanks for looking at me like I didn't write them correctly. So, okay, so this is the alpha, that's the beta. So the first one we want to put in is the Gilman. That's going to be the beta, right? So that's going to be the CH3. Now remember, there's two of these and then the cuprate, right? Copper and then the lithium. Second step, I want to add my electrophilic carbon. So I form the enolate and then have it react with that electrophilic carbon, right? Questions about this one? So the Gilman reacts, adds the methyl and gives me the enolate. Then the enolate reacts with the electrophilic carbon. And again, always good to count all your carbons. The second one, what's the key here? I'm looking at a 1, 2, 3, 4, 5 species. So that's suggesting that I have an enamine. I mean, I have a Michael or a Stort. But here I'm dealing with a single carbonyl. So as a single carbonyl, would a Michael give me a good reaction, good product mixture? No, it's probably going to give me several products, right? So therefore, what I want to use here is a Stort, which means first step, I'm going to use a secondary amine and, you know, just look for a secondary amine. Then I'm going to add my alpha beta unsaturated. And then last step, now I need to have, you know, acid and water to hydrolyze and protonate. So I hydrolyze off the enamine that I added, the imine I added, and then I hydrolyze the enolate back to the enol, which detomerizes to the final product. Okay, questions about this one? Okay, this one is just in a different format. I wanted to throw a different format at you. But what's really happening here? I'm making a ketone, right? And if I think about what I have over here, I have 4 carbons. And over here, right, I have 3 carbons, right, with the original 4 carbons. So which reaction, and it's a named reaction, which named reactions will add 3 carbons as a ketone? Well, that's the acetoacetic ester synthesis, right? So all I did was invert this. So I'm going to add the enolate so I'll add that, right? I could put it that way. I could have also shown it as, you know, this. That's going to do the addition, right? And then I just need to hydrolyze. Second step, I need to hydrolyze and decarboxylate. So the acid and water is going to hydrolyze the ester, and then the heat will decarboxylate. So this is a acetoacetic ester synthesis, just starting with the electrophile instead of the acetoacetic ester. Questions about this one? As you're practicing and as you're making practice problems for each other, this is a good way to throw a wrench in there and see if people really understand what's going on, right? I tend not to do that that often on exams, but it is a good way to practice. Look at it backwards and see if it still works, okay? All right, let's try a few more. Let's try a series of options. So if you start with this, how do I get to this? How do I get to this? And then how do I get to this? And similarly, if I start with this, and I'm not giving myself a lot of room here because I want to have you work on both of these at the same time. And how do I get that? So start with the same starting material. Let's add an alkyl group to the alpha or the beta or the alpha and beta. And then on the bottom one, let's add it to the most substituted side, the thermodynamic and the kinetic side. let's take a look at the first set. So the first step one, right? The first thing we're going to make is the enolate. And we want to make the enolate and have it stop, right? We don't want it equilibrium, or that's going to give us some aldol reactions. So we do full enolate with something like LDA, and then we add our electrophile, right? And I tend to put methyl iodide because methyl iodide is a liquid and methyl bromide tends to boil if you hold it in your hand for long. Then the second one, actually there's more than 2 steps here. So 2, 3, 4, right? First step we're going to have to do is bromide and acid. Second step, we're going to need to add a base. Okay, that'll give us the elimination of the alpha beta unsaturated. Then we can add our cuprate. And then our proton. Similarly, on this last one, we're going to have to make our alpha beta unsaturated. And here, your Chem 101 homer likes to use acetic acid. So that's the shorthand for acetic acid. So all we need is bromine and an acid. That's going to do the bromination at the alpha position. Then we can add a base to do the elimination. Third step here is the Gilman reagent. And fourth step, instead of adding acid and water, we'll add the electrophile. Okay, so the second two, what we have to do first is to form the alpha beta unsaturated. So that's what step 1 and step 2 are doing. So to form the beta addition and the alpha beta addition, we need the alpha beta unsaturated. Questions about that one? Okay, on this next one, this is thermodynamic and kinetic. So this top one is our thermo. The bottom one is our kinetic. Now for both of these, we want strong acids that will not form an equilibrium, right? So we don't want to add an equilibrium, because we add an equilibrium, what's possible? It can go back and forth between both of those. We want to form one and have it kind of stop. So for the first one, something like sodium hydride, but since we want thermodynamic, we want it at least room temperature, if not higher, right? And then we add our methyl iodide or electrophile. In the second one, we want something that's bulky and a low temperature. So LDA, right? And then minus 78 degrees Celsius, that'll give us kinetic. Oh, 1 and 2. Now we add our CH3I. Questions about those two? All right, let's get a little bit more advanced. And we'll have to do these quick, but I do want to show them to you. Actually, this should work on the top one. Okay, let's go ahead and take a look at this, mainly because my computer's fixing to break down and we're running out of time. So in this one, what we're going to do is brominate, right? So remember, bromine and acid. Then I'm going to protect. Then I'm going to react with sodium cyanide. Then I'm going to reduce that. And this should actually be, no, that's okay. It works out. And then H3O plus to deprotect. So we go to this. Now at this point, we could add the nitrile, but the nitrile has 2 electrophiles. So if I protect, I only am left with 1 electrophile. And then I can reduce that. And then deprotect. Okay. So we're finished with this chapter. So Tuesday we'll start on amines. So if you want to start reading through amines, and we will see you. There is another online homework assignment. So I think there's due one today, and then the new one over this material is up already. Y'all have a good day.